The operation begins with the careful dismounting of the mirror cell from the telescope structure, a process that requires absolute precision due to the size and sensitivity of the components involved. The mirror cell, which houses the 8.2-meter primary mirror, is first decoupled from the telescope's altitude structure. Specialized hydraulic supports and lifting equipment are positioned beneath the telescope to gradually bear the weight of the mirror cell, which weighs several tons. Engineers and technicians meticulously disconnect a network of control systems, cables, and actuators that normally keep the mirror aligned to nanometer precision during observations. Once all attachments are safely removed, the mirror cell is slowly lowered from its operational position within the telescope. Throughout this step, the process is continuously monitored in real time to ensure structural integrity and vibration isolation. The successful dismounting marks the start of the mirror's journey toward maintenance and recoating. Once safely dismounted, the massive mirror cell is carefully prepared for transport down the mountain to the base camp's mirror maintenance facility. A custom-built transport vehicle equipped with vibration-damping suspension and precise load-balancing systems is used to protect the fragile optics during the journey. The route from the telescope dome to the base camp winds down steep, narrow service roads on Cerro Paranal, requiring slow and deliberate movement under close supervision. A convoy of engineers, safety personnel, and escort vehicles accompanies the transport to monitor environmental conditions and mechanical stability throughout the descent. Every turn, bump, and slope is navigated with extreme caution to prevent even the slightest shock to the 22-ton mirror. The journey, although short in distance, can take several hours due to the painstaking care required. Upon arrival at the base camp, the transport vehicle carefully backs into the mirror maintenance building, where climate control, cleanroom standards, and overhead cranes ensure a safe, dust-free environment for the delicate operations ahead. Inside the mirror maintenance building, the process of dismounting the mirror from its cell begins with the removal of securing clamps and actuators that hold the mirror in place during telescope operations. Technicians work in cleanroom conditions to prevent contamination, using specialized tools to access and release the support points distributed around the mirror's edge and underside. Once fully detached, the mirror, still in a horizontal position, is prepared for lifting using a multi-point sling system that evenly distributes its immense weight. Lifting the 22-ton mirror is one of the most delicate phases of the operation. A specially engineered overhead crane equipped with a custom-built multi-point lifting frame is used to evenly distribute the mirror's weight and prevent flexing or stress. Technicians carefully attach the lifting slings to designated mounting points on the mirror's edge. With millimeter precision, the crane operator begins the slow ascent, while spotters monitor for any movement or imbalance. The mirror is gradually raised and suspended above the mirror's cell, ready for transfer to the coating facility. With the mirror securely suspended, it is slowly moved across the cleanroom and precisely aligned above the vacuum vessel of the coating plant. Using guide rails and laser alignment systems, the mirror is carefully lowered into the cylindrical chamber. The vessel is specially designed to accommodate the massive mirror, ensuring even spacing for uniform coating during the high-vacuum aluminum deposition process. Once inside the coating facility, the mirror undergoes an intensive washing process to remove dust, residues, and microscopic particles. Technicians use deionized water and specialized non-abrasive detergents, applied with precision spray systems, to cleanse the mirror's surface. Soft lint-free materials are used to gently guide water flow and prevent scratching. Every step is conducted under strict cleanroom conditions to maintain optical purity. To remove the old reflective layer, The mirror is treated with a carefully controlled acid solution that dissolves the thin aluminum coating without damaging the glass substrate. This step requires exact timing and chemical concentration to ensure uniform removal. As the acid is applied, the mirror's silvery surface visibly fades, revealing the bare, pristine glass beneath, ready for cleaning and a new reflective layer. As the acid solution is gently applied to the mirror's surface, viewers can witness a striking transformation. The highly reflective aluminum layer, which once gave the mirror its brilliant, silvery sheen, begins to dissolve before their eyes. This process, visible in real time, creates a mesmerizing visual effect, starting as small patches of dullness that quickly spread across the surface like melting frost. Within minutes, the uniform metallic reflection gives way to the clear, deep appearance of the underlying glass. Technicians monitor the process carefully to ensure that the acid acts evenly across the entire 8.2-meter diameter. The disappearance of the coating is more than just visual. It's a critical step that prepares the surface for a flawless new layer. Once the reflective layer is fully removed, the mirror is thoroughly rinsed with deionized water to eliminate any chemical residues, ensuring the glass is chemically clean and optically ready for the new coating process. The clean mirror is gently lifted and transported using precision cranes and alignment systems to position it inside the vacuum coater. Once the mirror is securely positioned, the massive vacuum chamber is sealed using a reinforced lid. High-powered pumps then evacuate the air, creating an ultra-clean, high-vacuum environment for coating. Inside the sealed vacuum chamber, the mirror undergoes the final and most critical stage of the process, the application of a new reflective coating. The chamber is evacuated to a high vacuum, typically around 10 to the power of 6 millibars, to eliminate all air molecules that could interfere with the coating process. This ultra-clean environment ensures the purity and uniformity of the aluminum layer to be deposited. The coating is applied through a method known as vacuum thermal evaporation. In this process, high-purity aluminum is placed in crucibles located beneath the mirror and heated using electric current or electron beam sources. As the aluminum reaches its vaporization point, it transforms into a cloud of aluminum vapor. With no air to impede it, the vapor travels in straight lines and condenses onto all exposed surfaces, primarily the mirror's front face. The large surface area of the 8.2-meter mirror demands precise control over the deposition rate and uniformity. Rotational systems or adjustable shutters may be used to ensure an even layer across the entire surface. The aluminum atoms bond directly to the glass, forming a new, highly reflective layer only a few hundred nanometers thick, just enough to reflect maximum light while preserving image clarity. Sensors and real-time monitoring systems track the coating thickness and uniformity throughout the process. Once the desired reflectivity is achieved, the aluminum source is turned off, and the mirror is left to cool inside the chamber. The result is a pristine, high-performance mirror surface, ready to return to astronomical duty atop the mountain. Once cooled and inspected, the mirror is reassembled into its cell, transported back up the mountain, and reinstalled in the telescope. This operation restores the VLT's optical performance, ensuring it continues capturing breathtaking images of the universe. The European Southern Observatory's ESO Paranal Observatory in Chile is home to the Very Large Telescope, VLT, one of the most advanced optical telescopes in the world. Maintaining its performance requires care, especially when it comes to recoating the massive 8.2-meter primary mirrors. Over time, exposure to dust and environmental conditions causes the mirror's thin reflective aluminum layer to degrade, reducing its ability to collect and reflect faint cosmic light. Recoating the mirror is a complex and high-precision operation that takes about 8 days and involves a highly trained team, specialized equipment, and a carefully coordinated workflow. The auxiliary telescopes at Paranal Observatory are relocated on rails between 30 stations to adjust interferometric baselines, enabling high-resolution imaging by combining light from multiple telescope positions. The mobile auxiliary telescopes move on rails between 30 stations, enabling flexible configurations essential for high-resolution interferometric observations. The auxiliary telescopes collect light and channel it through underground ducts to the Paranal Interferometer, VLTI, where beams from multiple telescopes are combined. This process of interferometry significantly enhances image resolution, allowing astronomers to observe fine details of distant celestial objects. To create a detailed image using interferometry, observations must be made with telescopes positioned in various configurations. Each configuration provides unique baseline lengths and angles, capturing different spatial information about the target. Regular relocation of the auxiliary telescopes between their 30 stations allows astronomers to sample these diverse baselines, combining data to reconstruct high-resolution images that reveal fine structural details of celestial objects. In this setup, the 4 auxiliary telescopes are positioned closely together to form a compact array, known as a short baseline configuration. This arrangement is ideal for observing larger, more extended celestial objects because it captures lower spatial frequencies, providing better sensitivity to overall shapes and structures. By reducing the distance between telescopes, astronomers can gather complementary data that, when combined with long baseline observations, contributes to creating a complete, high-resolution image of the target. Viewing an auxiliary telescope AT from below reveals the intricate engineering that supports its mobility and precision. The base houses the moving platform mounted on heavy-duty rails, allowing the entire telescope structure to glide smoothly between stations. Visible are the robust mechanical components, including motors and suspension systems, designed to absorb vibrations and maintain stability during movement and observations. The underside also features access points for underground light ducts that channel collected starlight to the VLTI beam combining facility. This sophisticated design ensures that despite being mobile, each AT maintains the precise alignment and structural rigidity necessary for accurate interferometric measurements. Relocating a single auxiliary telescope is a carefully controlled process that takes approximately 2 to 3 hours. This involves disconnecting the telescope from its current station, moving it smoothly along the heavy-duty rails, and precisely positioning it at a new location. These telescopes are the world's largest optical telescopes designed to move on tracks, combining massive size with mobility. After sunset, the auxiliary telescopes are carefully opened and prepared for nighttime observations. Protective covers and domes retract to expose the telescope mirrors to the night sky, allowing them to collect faint light from distant celestial objects. The telescopes then begin tracking targets with high precision, feeding light into the VLTI system. Night observations take advantage of the dark, clear skies at Paranal, enabling astronomers to capture high-quality data essential for interferometric imaging. Centering the drone is a crucial step to ensure precise alignment and stability before beginning any telescope operations. This process involves carefully adjusting the drone's position so that it is perfectly aligned with the telescope's field of view. Using Arcsecond.local, I fine-tune the drone's coordinates, making small incremental movements to achieve exact centering. This accuracy is essential for maintaining steady tracking of celestial objects and minimizing drift during observations. After months of simulator practice in France, this hands-on adjustment marks a key moment in bridging virtual training with real-world control here in Hobart. Playing with the telescope through Arcsecond.local has been both thrilling and deeply rewarding. Using this local web interface, I can interact directly with the telescope's motors, focus system, and alignment protocols. It allows for real-time control, from slewing to celestial targets to fine-tuning tracking speeds. After weeks of testing commands and refining scripts, seeing the telescope respond precisely to input feels like magic. This hands-on control transforms abstract code into visible motion, bridging software with the physical night sky in a seamless, intuitive way. The result of months of preparation in France with the simulator is finally paying off in the field. Back in France, I spent countless hours running virtual tests, troubleshooting control sequences, and simulating telescope behavior under various conditions. This phase was essential for building a deep understanding of the system's responses and for anticipating potential issues. Every line of code, every simulation run, helped create a solid foundation. Now, as I see the real telescope respond just as predicted, it's clear how vital that preparation was for today's success in Hobart. Now working after an intense coding month here in Hobart feels incredibly rewarding. I spent weeks refining control scripts, debugging hardware communication issues, and optimizing performance under real-world conditions. Each day brought new challenges, from firmware quirks to timing glitches, but persistence paid off. Seeing everything finally operate smoothly confirms the value of every long, focused coding session. Creating a DIY vacuum chamber for coding telescope mirrors is a challenging but rewarding project that allows amateur astronomers to apply reflective coatings, such as aluminum, to their mirrors at home. It requires precise control over vacuum pressure, power supply, and timing to ensure a uniform and successful coating. The first step involves preparing the vacuum chamber and activating the vacuum pump. Once the mirror is securely placed inside the chamber and all components are sealed, the vacuum pump is turned on. The system is then allowed to run for approximately 45 minutes. This period is crucial as it ensures that the chamber reaches the required low-pressure environment. Achieving a pressure of around 10 to the power of minus 5 to 10 to the power of minus 6 torr is ideal for effective aluminum vapor deposition. During this time, it's important to monitor gauges and check for any leaks in the system. After the chamber has been evacuated to the desired vacuum level, the next step is to initiate the power to the evaporation source. In most DIY setups, this involves a tungsten filament loaded with aluminum wire. Once a sufficient amount of aluminum has been deposited on the mirror, typically after a few minutes, the power is turned off. At this point, the filament cools down, and the aluminum evaporation ceases. It is crucial to allow the mirror and other chamber components to cool before breaking the vacuum. This helps prevent oxidation of the freshly coated surface and minimizes the risk of contamination. After powering off and allowing the system to cool, the vacuum can be slowly released, the chamber is opened, and the mirror is carefully removed. A successful coating will appear as a bright, even, and highly reflective surface on the mirror. The quality of the coating can be checked visually and with optical tests. If done correctly, the mirror will now be ready for installation in a telescope, dramatically improving its light-gathering capability. Building and using a DIY vacuum chamber for telescope mirror coating requires careful planning and attention to detail, but can yield professional quality results for dedicated amateur astronomers. Recoating the mirrors of large binocular telescopes is a critical maintenance procedure that ensures optimal reflectivity and image quality. Over time, telescope mirrors accumulate dust, oxidation, and microscopic degradation of the reflective surface, leading to diminished performance. To restore them, the mirrors are carefully removed and placed into a high vacuum recoating chamber. The process begins with cleaning the mirror to remove all contaminants. Once cleaned, the mirror, often as large as 180 millimeters or more in diameter, is secured inside the vacuum chamber. The chamber is then sealed, and the vacuum pump is turned on. Within approximately 25 minutes, the pressure inside drops to the required vacuum level, often below 10 to the power of 6 torr, creating a contamination-free environment ideal for vapor deposition. In the coating phase, a thin layer of aluminum or silver is thermally evaporated onto the mirror surface. The high vacuum allows the metal vapor to travel in straight lines and uniformly deposit onto the mirror. This results in a smooth, highly reflective coating, essential for precise astronomical observations. To protect the reflective layer, a thin overcoat of protective materials such as silicon dioxide, silicon oxide, is often applied. A 180mm mirror, while small compared to the 8.4-meter mirrors in the large binocular telescope, still undergoes the same meticulous recoating process to ensure optimal performance. After recoating, the chamber is slowly returned to atmospheric pressure, and the mirror is carefully removed and inspected for uniformity and defects. The entire process, from pumping down the chamber to completing the coating, requires precise control and timing. Mirror recoating using a vacuum chamber ensures the high reflectivity and optical clarity needed for deep sky observation, and is a vital part of maintaining any high-performance telescope system.